Okay, this is the lecture video for MAC 1105. We're in section 4.3 where we're going to discuss the remainder and factor theorems. This section has very much to do with division of polynomials, and while we're going to be concentrating on synthetic division for the most part, I also want to reintroduce long division and make sure that you can handle both kinds of division. So let's start with examples 1 and 2, where we're going to be looking at the steps for long division concerning polynomials. First, we'll start with some terminology. This is called the dividend. This is called the divisor. And you're going to set up your long division. These are the steps all written out for you, all typed out for you. But I'm going to give it, give you my own take on how to do this. And first thing you're going to do is set up your dividend inside a division box, and the divisor will go outside. These terms underneath the division box need to be in descending order. So highest degree, then next highest, then next highest, all the way down to the constant. So you do need to rearrange those. Highest term first. Okay, so here I am setting myself up for the division. I'm going to put the cubed term first, then the squared term, then the first degree term, then the constant. Okay, I'm dividing by 3x minus 2. Okay, and when you do long division, you're always going to be concentrating on the leftmost term of the divisor and trying to turn it into the leftmost term of the dividend by way of multiplication. So you have to ask yourself, what do I multiply this by to turn it into this? And that would be 2x squared. Once you come up with a term of what's called the quotient, that's this expression that you're getting right up here. Once you come up with a term of your quotient, you're going to take that term and multiply it by everything in the divisor. Okay, so 2x squared times 3x, 6x cubed, because you're going 2 times 3 to get the 6. X squared plus x to the first degree is x to the third. 2x squared times negative 2 is negative 4x squared. You want to make sure that you're lining up like terms. In other words, same variable, same exponent. Third step, after coming up with a term of your quotient, using it as a multiplier, that third step would be subtract the bottom row, which really just means switch the signs and then combine it with the row above. That's the same thing as subtracting the bottom row from the top row. So 6x cubed combined with negative 6x cubed cancels. Negative 1x squared plus 4x squared. Negative 1 plus 4 is 3 on your x squared term, and then drop one more term down and go again. We're going to repeat those 3 steps until we can't go any further. So once again, concentrate on the leftmost term of the divisor and the leftmost term of this expression below the bar. And ask yourself, what do I have to multiply this by to turn it into this? Well, you'd need an additional x. 3x times x would be 3x squared. So multiplying by x would turn this, when you multiply by x, into this. So x, now each time you come up with a new term of your quotient, you go through this multiplication, this distribution step. So it's now, I just don't want to keep drawing arrows. So x times 3x would be 3x squared. X times negative 2, negative 2x. And then subtract that bottom row by just switching the signs. You should circle your switch sign so that you can focus on the sign you're really supposed to be using. So it's positive 3x squared combined with negative 3x squared. That leftmost column should always cancel if you did the steps properly. Negative 5x combined with positive 2x is negative 3x, and drop down one more term. Okay, go one more time. You can still go one more time because what would you multiply 3x by to turn it into this? Again, working with the leftmost terms only when you answer this question. You'd have to multiply this by -1 to turn it into this. So the answer to what you need to multiply by to turn this into this is what goes up here in the quotient. It is your next term, and each time you get a new term, you take that new term and multiply it by every term in the divisor. So -1 times 3x is -3x. -1 times -2 is +2. And subtract that bottom row by switching the sign of each term in the bottom row and combining with the row above it. So -3x combined with +3x is gone. +4 combined with -2 is 2. So in the end, your answer is 2x squared plus x minus 1 plus your remainder. And sometimes, the software you're using, My Open Math in your case, sometimes it'll be My Math Lab. Sometimes they'll offer you a separate box to just give the numerator of your remainder. So they'll just say, what is the remainder? And you can just say 2. And then sometimes they want you to give it in rational form. In other words, fractional form. So this is your quotient. This is your remainder. And that's how you write the quotient combined with the remainder. You just add on the remainder, but in fraction form. It'll be the remainder, which is what you see here, over the divisor. Okay, that's one example doing long division. This next example is also long division, only they just present it to you differently. This time they're presenting the division problem as a fraction, but I think we've all had enough experience at this point that you understand that this means this expression divided by, that's what this fractional bar means, the bottom expression. So this would be your dividend, and it goes, underneath the division box, and this will be your divisor. Don't forget that this dividend needs to go in descending order, highest power all the way down to the lowest power. Now I chose this particular problem because it is also important that you replace any missing powers that you might have. Like this, the first problem that we had did not have any missing powers, any missing exponents you could call it. But this one does. In other words, let me point that out to you. It goes 4th degree, 3rd degree. It is missing the 2nd degree term. So it is said that you have 0 of these. What sign you put in front of it is up to you because 0 is signless. It doesn't have a sign. It's the only number that doesn't have a sign. So it doesn't matter whether you put a plus or a minus in front of it. Just put one or the other. I'm just going to put a plus. Anyway, this will serve as a placeholder so that in the mechanics of the problem, if an x squared term does show up by way of the multiplications and other operations that you do, you'll actually have a column to put it in, to line it up with. So that's why you never skip over any powers, even though the original problem may do that. You replace missing powers with what's called a dummy variable or a space holder. Okay, so here we go with the actual long division. We're going to go in descending order. So this is our highest degree. Next highest degree is the 5x cubed. Next highest degree is the one that was missing. I'll just write it that we had 0 of the x squared term with a plus sign in front of it. Next term was our 1st degree term, and last term was our constant. Our divisor, you don't have to put any missing variables in there, or missing exponents anyway. You can just use it as is. And let's start doing the problem. Again, what I demonstrated on the first long division problem is that you're always looking at the leftmost term in the divisor and trying to turn it into the leftmost term in the dividend, or the expression that turns out below the bar. We haven't gotten that far in the problem yet, by way of multiplication. So what do I multiply this by to turn it into this? 2, and you would need a couple more x's. That combined with that would give you the x to the 4th. Once you come up with a term in your quotient, you're going to multiply it by all terms in the divisor. Each and every time you come up with a new term in the quotient, you will do this. So 2x squared times 3x squared is 6x to the 4th, and then 2x squared times negative 2x is negative 4x cubed. And then that third step is subtract by switching the signs of each of the terms on the bottom row. This combined with negative 6x squared, that cancels. Positive 5 combined with positive 4 is 9x cubed. 9 on that x cubed term. Drop down the next term. Even though there's 0 of them, this is going to act as a placeholder, because we are going to get x squared terms as we go on to the next step. Okay, so let's start all over again. This is our second pass through the long division problem. We want to know what to multiply this by to turn it into the leftmost term here. So we're still working with that dividend. It's just that this is what the portion of the dividend that we're working with right now. What do you multiply this by to turn it into this? Just keep eyeballing those leftmost terms, and that will be, you'd have to multiply by 3 to get that, and I'd need another x. So 3x. Have a new term here, so now multiply this 3x by everything out in the divisor. So 3x times 3x squared would be 9x cubed. 3x times negative 2x would be negative 6x squared. And subtract that bottom row by switching the signs on the bottom row and then combining them with the row above. So 9, take away 9, that would be gone, your x cubed terms. 0 plus 6 on your x squared term would be 6x squared, and drop down one extra term. And go again. So what do you multiply the leftmost term by here to turn it into the leftmost term down here? You'd have to multiply by 2 to get this 6, but you don't need any more x's. So plus 2. Once again, I have a new term in my quotient, and I have to use it to multiply by everything in the divisor, each and every term in the divisor. So 2 times 3x squared, 6x squared. 2 times negative 2x, negative 4x. And then subtract that bottom row by switching the signs of each of the terms and combining with the row above it. So 6x squared minus 6x squared cancel. 3x plus 4x, 7x, and then bring down that negative 5. Okay, when the degree here is lower than the degree here, there's no way to go any further, because what could you possibly multiply by that's going to bring it down to first degree? You're not allowed to use negative exponents, so you stop here. When the degree here is less than the degree here, stop. This would be the remainder. It just happens to have a variable in it. So the quotient is 2x squared plus 3x plus 2 plus your remainder. 7x minus 5 written in fraction form over the divisor. 3x squared minus 2x. And that would serve as your final answer. Okay, moving on to synthetic division and all the things that we're going to do with synthetic division in this section. So we can use synthetic division just to do, a shortened version that happens much more quickly, as my comments state right here. When you're doing synthetic division, you're getting rid of the variables while you're going through the procedure of division. So it works like this. When you are asked to divide by x minus 3, of course, this is your divisor, and this is your dividend. Okay, just like we had names when we were doing long division. This is your dividend, and what you're dividing by is your divisor. So you're only going to be using numbers in this particular procedure, not the variables. So you're going to be using this in the divisor box. And anytime you take an expression and you break this constant apart from the actual variable, you're going to break these two apart, you must switch the sign on the constant. Only when it is attached to a variable before delivering it to the divisor box. So instead of -3, +3. Then you're going to take the coefficients, just the coefficients, not the variables, of each of these terms. Make sure that you're not skipping over any exponents. This goes third degree, second degree, first degree, constant. So this is in perfect order. You're not missing anything. You don't need any placeholders. Just like I discussed those placeholders in that problem where I put 0x squared, which was actually in this problem right here. Same thing is true here. You need placeholders if you're missing one of the powers, but we don't have that happening. I'll demonstrate it when we do. And you're only going to be using the coefficients. Coefficient of the third degree term is 1. You're going to space them out horizontally. Coefficient of the second degree term is 4. Coefficient of the first degree term, -5. Coefficient, and then this is just a constant. You could call that the coefficient of the 0 degree term, or you can just call it a constant. Draw a line under these numbers, leaving space under each one for the numbers that we're going to get in this synthetic division procedure. The synthetic division procedure starts by you dropping the very first value below the bar and then multiplying what's in the division box by the number that's below the bar, and you're going to continue to do that until you get to the remainder. The remainder will be the number in the last column. Each time you get a number below this bar, you'll multiply by this and carry the answer up here and then combine them. So I'll demonstrate that. 3 times 1 is 3. Carry it up here and combine these two. 4 plus 3, 7. Go again. Now it's 3 times 7, which is 21. Combine these, you get 16. Then it's 3 times 16. 3 times 16 is 48. And then you'll combine these and you'll get 53. So 53 is actually your remainder. Hold on for 1 second. My power cord just got disconnected. Okay. Okay, so when you go to give your answers for for problems that you've done by synthetic division, you want to state your quotient, and you also want to state your remainder. This is your quotient when you're using this style of division for polynomials, and this is your remainder. But you need to reattach the variables. So each time you make a synthetic division pass through the whole polynomial, where you have synthetically divided it by a number, you decompress the original polynomial. Original polynomial was third degree. By the time you take a single pass synthetically dividing 3 into all of these, it brings it down to a second degree polynomial. It brings it down by a degree. So in other words, this 1 that you're seeing is the coefficient of your second degree term. This next number is the coefficient, it's a +7, of your first degree term. Each successive term is 1 degree less than the one in front of it. The 16 would therefore be the 0 degree term, or what we call the constant. So second degree, first degree, 0 degree. And then this 53 is just your remainder. Remainders can be written. It's not unusual. It's actually a common way for remainders to be written as a fraction. So 53 over the divisor, which was originally given as x minus 3. So in a much cleaner and much quicker way, you are able to find the quotient as well as the remainder. Okay, moving to the next example. Use synthetic division to divide 5x cubed plus 6x plus 8 by x plus 2. So we're going to take all the coefficients and arrange them horizontally. This value that's going to be in the division box, the synthetic division box, is attached to an x, and therefore you are going to switch the sign as you break this value apart from the variable. Only when it's attached to an x will you switch the sign. I also noticed that in this problem I am missing my x squared term, so I have 0 of those. So when I go to prepare my synthetic problem, I'm going to be putting a -2 in my synthetic division box, and I'm going to be stretching out the coefficients going in descending order. So my x cubed term, coefficient is 5. My second degree term, the coefficient is 0. My first degree term has a coefficient of 6, and then my constant is 8. I put a line underneath those values, leaving space for the values I'm going to get when I multiply. We begin by dropping the first value below the bar, and then starting the multiplication process. So -2 times 5, -10, combine these two numbers. -2 times -10 would be 20, and combine these two numbers. And then -2 times 26 is -52, and then -52 plus 8 is -44. Okay, so each time I multiplied by -2 until I got to the last column. So drop down the 5. -2 times 5 is -10. -2 times -10 was 20. Add those up, we got 26. -2 times 26 was -52. This added to this is -42, and that last column is always your remainder. Don't forget to, as you present your coefficients, do not just give a string of numbers. You want to reattach the variables. Put those variables back on. Remember that as you take that synthetic division pass through this problem, you're decompressing it. So if the beginning term or the highest degree was third degree in the original problem, you are now down a degree. So this first number represents the second degree term. This next number represents the first degree term, because this will be 1 degree less than that. This next number represents the constant, and then your coefficient is -44 divided by x plus 2 if you want to give your remainder, in fractional form. Okay, the remainder theorem. The remainder theorem is just a new way to do substitution. This says if a polynomial is divided by an expression x minus c, and you know that when we divide by an expression x minus c, we simply switch the sign of this value and deliver it to the division box. Then the remainder is the same as if you had plugged c into the original function. So this becomes a new way of doing substitution rather than going through all the steps that you might have to go through in a polynomial that has many terms with many powers on it. This will be a new way for you to do substitution. So we are going to be finding f with 2 plugged in, but instead of plugging it in here, we're going to use a synthetic approach. The value 2 that we're plugging in, notice that it is not part of an expression x minus 2 or x plus 2, where you're breaking them apart and switching the sign. So because that is not the case, you're going to deliver the number as is with respect to the sign. But you're still going to be using the synthetic procedure. So we're going to deliver a +2, just like you see a +2 there, into this division box. We're going to stretch out the coefficients, 1 for third degree, -4 for second degree, 5 for first degree, and 3 for my constant. We're going to leave room underneath those values. begin by dropping the first value and multiplying. So it's 2 multiplied by that first value. 2 times 1 is 2. Put that right up here and combine. Then it's 2 times negative 2, which is negative 4, and combine. Then it's 5 combined with negative 4. That would be a 1. We're going to multiply by 2 again. And this would be 2 times 1 is 2. Bring it up there and combine. Okay, so just checking this real quick. I dropped a 1. I went 2 times 1 is 2. Added those, got a negative 2. Went 2 times negative 2 is negative 4. Added those and got a 1. 2 times 1 is 2. Added those and got a 5. And let's remember that now what we're doing is we're using the remainder theorem. And what this says is that the remainder is actually the answer you would have gotten if you would have plugged 2 in here, 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 everywhere there was an x. So you can do that if you want to, but that's just a lot more work, even if you do press it in your calculator, because you'd have to plug that in, then you'd have to plug in negative 4 times 2 squared, then you'd have to plug in a 2 again here, and then you'd have to add 3. So by the time you press in all those multiplications and powers into your calculator, it's kind of a hassle. I think you get the answer much quicker here. So what this is saying is that f of 2, because you got a remainder, the answer to all of this is going to be exactly what you got for your remainder. This is just a lot more work, and this is a new way to do substitution. Okay, so that just came from me looking at what my remainder was. Okay, now we can use what's called the factor theorem in order to help us completely factor a polynomial of higher degree, like 3rd degree, 4th degree, 5th degree even. And we can go, we can use this theorem in order to understand what we are getting. What this says is that if you get a remainder of 0 when you do synthetic division, I'm just reinterpreting these for you so you can understand them. If you get a remainder of 0 when you do synthetic division, then you are finding the factors of the polynomial, and that enables you to find the solutions, what we also call zeros. Zeros means the same thing as solutions. When you're on a graph, it also means the x-intercepts. These are all interchangeable terms. They all mean the same thing. Okay, so when you find the factors of a polynomial, that will allow you to find the actual solutions of the polynomial. And all you have to make sure is that when you do your synthetic pass, you get a remainder of 0. Okay, so in this particular problem, it says use synthetic division to divide this polynomial by x plus 3. Now we see our 3 being attached to an expression containing x, and that's our clue to switch the sign before delivering it to the synthetic division box. So we are going to be delivering a negative 3 in that synthetic division box. Make sure that none of the powers are missing. We have 3rd degree, 2nd degree, 1st degree, and then we have a constant. So all degrees are present. We don't need any kind of a space holder, and we are using just the coefficients. Coefficient of the 1st degree term, of the 3rd degree term, excuse me, is a 1. Coefficient of the 2nd degree term is a 7. Coefficient of the 1st degree term is a negative 9. And the constant is negative 63. I put that line here. Try and make my 7 look more normal. Not so big. And we're dividing by x plus 3, which is why we delivered a negative 3 into that synthetic division box. drop down the first term and begin that multiplication. Negative 3 times 1, negative 3. Add these terms up, you get 4. Negative 3 times 4 is negative 12. Add these up, you get negative 21. Negative 3 times negative 21 is positive 63. And notice that this remainder has zeroed out. When the remainder is 0, that means that we have brought this down and to the next lowest degree. And not only that, they are factors that are going to help us find the solutions to this polynomial equation. So, one thing that you are finding by this zeroing out is you're finding out that this itself, anything that zeroes out when you are doing synthetic division, that's not only a factor, but it also is a solution. So one of the solutions is negative 3. It can be written as a factor, which is what all this is talking about. Like for instance, this function that you saw originally, x cubed plus 7x squared minus 9x minus 63, it can be written like this. This would be the factor that corresponds to this solution. When they're in factor form, they have the opposite sign as what the numbers have when they're reported as solutions. So here is going to be my set of solutions, and here I'm just writing this in factored form. And what you see right here underneath this bar is the remaining equation after you have synthetically divided negative 3 into the original polynomial. So what remains is, remember, you have come down to second degree. So what remains down here is 1x squared. That's your second degree term. This is your first degree term. This is your constant. So what this is 1x squared, positive 4x, and then negative 21. Now we already know what the solution is that corresponds to this, also known as a 0. It is the value that zeroes this out, x equal to negative 3. It's already been reported here. I want to get the other zeros. I want to find all the zeros of the polynomial. So what I could do is continue factoring this. This is a trinomial. I want to bring it all the way down to first degree, to 2 first degree factors, just like this is a first degree factor, because then it is very easy to get those solutions. This one we already knew about, and we knew it was a solution because it zeroed out, which means it's an actual solution. So now factoring this, what times what is x squared? X squared. Then to get the proper numbers in the back, it's like a 2-part puzzle. What 2 numbers can be multiplied to give you this constant? But those same 2 numbers need to add up to this value in front of the linear term. Okay, the things that would work there would be, let's see, we could do 7, let's see, things that would work there, 7 and 3, and we can make one of them negative and one of them positive. This is the proper step to try and check who gets the negative, who gets the positive. If we were to make the 7 positive and the 3 negative, this plus this, and I'm coming up with these numbers based on things that multiply to give you 21, negative 21. But it's this step that allows you to determine who gets the negative. Larger number should have this sign. So if you're trying to get a positive 4, you want the larger number to be positive so that it's the ruling sign. Notice that when you multiply those 2 numbers, you not only get a negative 21, but you also get a positive 4. And the numbers you're choosing must satisfy these 2 steps. You should be able to multiply the 2 numbers to get the C value, but add the 2 numbers that you come up with just by knowing your times tables. You should be able to add them up to come up with the B value. Okay, and you can put whichever one you want first. But the point being is that you have now brought this second degree expression down to 2 first degree expressions, and at that point you can tell what the solutions are. The solutions are the numbers that make these factors 0. So what would zero this out? X equal to -7. So we have another answer. We found one of them by synthetic division. We synthetically divided -3 into the original polynomial, which came from this, and we found out that -3 causes a remainder of 0, and that verifies that it's a solution. It also helped us to bring this down to a second degree polynomial, which is right here, and we continued to factor it to bring it down to factors that looked like this one. And now we can just look at them and say, okay, what would make this 0? -7. So that's another answer for us, another solution, or what we call a 0. And then look at this factor, and the value that would make this factor equal to 0 would be +3. So you have all 3 solutions. Okay, that's going to be it for this particular video, and I will finish the rest of the problems from section 4.3 in the next video.